Scientists believe TRAPPIST-1e could be a real candidate for life, and that is the terrifying part. It orbits a small violent red dwarf, may be tidally locked, and may still have just enough atmosphere to stay in the game. If life can exist on a world like that, then the universe may be stranger than we thought. TRAPPIST-1e is a terrestrial planet with a radius about 0.92 times Earth's and a mass about 0.692 times Earth's. It completes an orbit in about 6.1 days. It circles its star at just 0.02925 astronomical units. If you think in solar system terms, that sounds wrong immediately. A year that short and an orbit that close should mean a ruined planet. It should mean a surface with no real chance of staying temperate. But that assumption breaks here because the star is not like the Sun. It is much smaller and much dimmer, so a distance that would mean disaster in our system can mean possible habitability in this one. That is why TRAPPIST-1e became such a major target after the system announcement in 2017. It sits in the most important position in the whole lineup, the place where, if the atmosphere is right, liquid water could exist. That does not mean liquid water has been found, does not mean life has been found. It means the planet occupies the exact kind of orbital slot that scientists have to take seriously. And that is enough to make it one of the most important rocky exoplanets ever discovered. This is also not a fantasy world built from one dramatic paper and a few nice illustrations. TRAPPIST-1e is one of the best characterized rocky exoplanets we have outside the solar system. Scientists did not just notice it once and move on. They have measured this system again and again using transits, transit timing variations, and now Webb spectroscopy. They know the planet is real. They know its size well enough to compare it to Earth. They know its mass well enough to say it is not some inflated mini Neptune hiding behind optimism. They know its orbit well enough to model how much energy it gets from its star. And every time those constraints improve, the central mystery stays alive. That is what makes this planet different from the average exoplanet headline. A lot of exoplanets are still broad outlines. TRAPPIST-1e is a specific case. It belongs to a compact 7-planet system that has been measured hard enough for the remaining unknowns to matter. This is not a situation where almost everything is unclear. This is a situation where enough is known that the unknown parts become more important. Once science gets to that stage, the conversation changes. You are no longer asking whether the planet is real, you're asking what kind of world it actually is. And this is where the story gets more unsettling. If TRAPPIST-1e is habitable, it probably is not habitable in a comfortable, Earth-copy way. It may be tidally locked, with one side facing the star all the time and the other side in permanent darkness. It may have a heavier atmosphere than Earth, if it has an atmosphere at all. It may sit under frequent radiation stress from a volatile red dwarf. It may only support liquid water in limited regions instead of across a broad, stable surface. So the serious implication is not just that life could exist there. The serious implication is that life, if it exists there, may be able to survive under conditions that most people would have assumed were too unstable, too harsh, or too strange. That is the part that pushes this beyond a normal exoplanet story. People often use the phrase Earth-like, as if that is the same thing as possibly habitable, but those are not the same idea. Earth-like usually means familiar star, familiar orbit, familiar climate logic, familiar day-night behaviour. TRAPPIST-1e challenges that whole package. It asks whether a planet can stay relevant to the habitability discussion even when almost every major condition looks unfamiliar. Different star, different year, different radiation environment, probably different rotation state, possibly different atmospheric structure. And still the question does not go away. So the title is wrong, but the real version is stronger. Scientists are not saying there is life on TRAPPIST-1e. They are saying this is one of the best planets we have ever found for testing whether a rocky world around a red dwarf can stay in the game. That sounds more cautious, but it has bigger consequences. Because if a planet like this can keep the right conditions long enough for liquid water, climate stability, and complex chemistry, then the universe may be making potentially living worlds in ways we did not prioritize before. That is why TRAPPIST-1e matters so much. It is forcing astronomers to test whether Earth-like was ever the right standard in the first place. Maybe a habitable world does not need to look familiar. Maybe it does not need a sun-like star. Maybe it does not need a long year or a balanced light cycle or a climate that makes immediate sense to you. Maybe those were just the conditions of one inhabited planet, not the rule for all inhabited planets. And if that turns out to be true, then this small world about 40 light-years away is not just another exoplanet. It is a direct challenge to the way we have been ranking possible living worlds. And the next part of the story makes that challenge even harder, because the star changes everything. In our system, a 6-day year would mean a dead world. Around TRAPPIST-1 it means maybe. That one fact is where the normal intuition breaks. This is where the whole story changes, because TRAPPIST-1 is not just a smaller version of the Sun, it is a different kind of star. It is an ultra-cool dwarf, which means it is tiny, faint, and much weaker in total light output than the Sun. And that one fact changes the meaning of distance, heat, and habitability all at once. In the solar system, if a planet completed a year in about 6 days, you would throw it out immediately. You would assume the surface was being cooked. Around TRAPPIST-1, that same kind of orbit does not automatically mean death. Around this star, it can still mean maybe. That is the first thing you need to lock in. TRAPPIST-1e is extremely close to its star by normal standards, but normal standards are the problem. This star is so dim that the habitable zone is pushed inward very tightly, so a planet can orbit absurdly close and still receive an energy level that keeps it in the serious habitability discussion. That sounds wrong at first because your intuition was trained by one star, one planetary system, and one example of life, TRAPPIST. One breaks that intuition fast. It shows that a close orbit does not always mean a destroyed world. Around a red dwarf, a close orbit can be the only place where conditions are even remotely workable. That already makes the system unusual, but the next part makes it much more important. This is not a young system that just formed and has not settled down yet. The star is estimated to be about 7.6 billion years old, with an uncertainty of about 2.2 billion years. That is a serious amount of time. It means TRAPPIST-1 is older than the Sun. So when people ask whether TRAPPIST-1e could have an atmosphere or some remaining water, they are not asking whether it could briefly hold on to those things for a short period right after formation. They are asking whether a rocky planet near a red dwarf could survive for billions of years under conditions that are supposed to be difficult. That changes the question from formation to endurance. A lot of worlds can look interesting for a while. The harder question is whether they stay interesting after long exposure to a difficult star. If TRAPPIST-1e has kept anything like a meaningful atmosphere over that kind of timescale, then it is not a temporary accident. It is a survivor. And if a planet can survive like that under an ultra-cool dwarf, then the entire red dwarf habitability debate gets more serious. Because red dwarfs are everywhere. They are the most common stars in the galaxy, so one planet holding on under one of these stars would not stay a local curiosity. It would immediately affect how we think about a huge fraction of the Milky Way. That leads to the next inversion. The habitable zone in this system is brutally close to the star. NASA has stressed this point over and over for a reason. All 7 known planets orbit closer to TRAPPIST-1 than Mercury orbits the Sun, and yet some of them are still in or near the habitable zone, because the star is so cool and dim. That single comparison is enough to reset the whole picture. If you say closer than Mercury, most people think the case is closed. But here, that distance does not mean a scorched rock by default. It can mean a world getting something closer to temperate levels of starlight. That is one of the hardest ideas in this whole story, because it forces you to stop using solar system language as if it applies everywhere. In our system, the habitable zone sits much farther out because the Sun is much brighter. Around TRAPPIST-1, that zone is compressed into a very small space. So the same physical distance can mean radically different outcomes depending on the star. Distance by itself is not the real measure. What matters is the energy the planet receives, the kind of radiation it receives, and how the planet responds to it. Once you understand that, TRAPPIST-1e stops looking like a contradiction and starts looking like a direct challenge to lazy assumptions. But even that does not tell the full story, because the light from a red dwarf is not just less intense, it is different in character. A cooler star like TRAPPIST-1 gives off more of its energy at longer wavelengths compared with the Sun. That matters because atmospheres and surfaces do not absorb all kinds of light in the same way. So even if TRAPPIST-1e gets about 0.66 times the stellar energy Earth gets from the Sun, that does not mean its climate behaves anything like Earth's climate. The source spectrum is different, the orbit is different, the likely rotation state is different. The atmospheric chemistry, if there is an atmosphere, may be very different. So you cannot take one number and pretend the case is solved. This is where the word habitable starts to lose its simple meaning. People hear that a planet gets less than Earth's starlight but still sits in the habitable zone, and they picture some colder version of Earth. That is too simple. TRAPPIST-1e may not have a regular Earth-like day. It may be tidally locked. It may move heat very differently between its day side and night side. It may respond to infrared heavy starlight in a way that creates cloud patterns, circulation systems, or temperature zones that do not resemble Earth at all. So when you say the planet gets a roughly plausible amount of energy, that is only the beginning. Same energy budget does not mean same climate. Same climate does not mean same surface conditions, and same surface conditions definitely do not mean same habitability path. Now the contradiction gets sharper. TRAPPIST-1 is exactly the kind of star that makes these planets easier to find and much harder to understand. Because the star is small, each planet blocks a larger fraction of its light when it transits. That gives astronomers strong signals and makes this system observationally valuable. A compact rocky system around a tiny star is one of the best setups we have for studying Earth-sized exoplanets at all. That is the good side of the story. The bad side is that the same star may be physically hostile to those planets and can also contaminate the data we use to study them. So the star gives you access and takes clarity away at the same time. It makes the planets detectable, but it may also blast them with flares, high-energy radiation, and magnetic activity that strip atmospheres or reshape them over time. It gives clean-looking transits in one sense, but it also covers the whole investigation in noise because the spots, flares, and surface activity can interfere with the spectra astronomers need. That is why the answer stays incomplete. The star is not just the background object in this story. It is the main reason the planets matter, and the main reason they are so difficult to read correctly. That is the core tension of TRAPPIST-1e. The system is observational gold because the star is small and the planets are packed in tightly. But the same setup may create exactly the kind of long-term stress that could strip a rocky world down to almost nothing. So when you look at TRAPPIST-1e, you're not looking at a simple habitable zone candidate. You're looking at a planet caught between two opposite conclusions. One conclusion says red dwarfs might host huge numbers of viable rocky worlds. The other says they may damage those worlds faster than hope can keep up. And that is why this star changes everything. It forces you to accept that the best places to search can also be the hardest places for a planet to survive. It forces you to separate easy to detect from easy to keep habitable. And it sets up the next problem, because once you realize how strange this star is, the obvious question becomes even more intense. If the system is this compact, this measurable, and this unlike the solar system, how do scientists know so much about a world they still cannot actually see? The strange part is that scientists know a lot about TRAPPIST-1e without ever seeing it directly. There is no clear photo of this planet. No telescope has captured oceans, clouds, continents, or a glowing atmosphere around it. That is not how this discovery works. TRAPPIST-1e first showed up by taking a tiny amount of light away from its star. When the planet passed in front of TRAPPIST-1 from our point of view, the star got slightly dimmer for a short time. That small dip in brightness is the entire starting point. From that dip, astronomers could work out the planet's size, From repeated dips, they could work out how long the planet takes to orbit. So the story does not begin with a picture. It begins with shadows, timing, and very precise measurements. That is how the whole TRAPPIST-1 system broke into public view. Observations from the TRAPPIST telescope from Spitzer and from ground-based observatories kept catching these repeated light drops. And once the signals were lined up properly, the now famous seven-planet system emerged. That matters because it shows this was not a guess built on one weird data point. Multiple instruments kept seeing the same behaviour. The planets were introducing themselves in a measurable way. Every time one crossed in front of the star, it left a small but detectable signature. That is why the system went from interesting to extraordinary so fast. Scientists were not just hearing a rumour from deep space, they were watching a pattern repeat. But a planet's size and year are not enough. The next question is harder. How do you estimate the mass of a world you cannot see in many systems? That part is difficult, especially for small rocky planets. TRAPPIST-1 is different because the planets are packed extremely close together. They do not orbit quietly and independently. They keep pulling on each other with gravity. Those pulls slightly shift the exact times when the planets transit the star. Sometimes a transit happens a little early, sometimes a little late. That is called transit timing variation, and in this system it is not some extra detail added after the main discovery. It is central to the whole case. This is one of the most impressive parts of the TRAPPIST-1 story, because scientists are effectively weighing invisible planets by watching them disrupt each other's schedules. The worlds are close enough together that gravity becomes visible through timing. You do not see the pull directly, but you see its consequences. And once you can measure those timing shifts well enough, you can estimate how massive the planets must be to cause them. That is how TRAPPIST-1e stopped being just a dot in a light curve and became a physical world with a measured size, a measured orbital period, and a meaningful estimate of mass. That combination changes everything, because once a rocky exoplanet has both size and mass constrained, scientists can start asking much more serious questions about its composition, density, atmosphere, and climate possibilities. That is why TRAPPIST-1e feels more solid than most exoplanets in public discussion. A lot of exoplanets are still broad categories. You know they exist, but the uncertainties are big enough that almost any interpretation can still sneak in. TRAPPIST-1e is not like that. Its period, orbit, radius, and mass are constrained well enough that researchers can run detailed models instead of just listing possibilities. They can study whether it is likely rocky. They can model how much energy it receives from its star. They can test whether different atmospheric pressures might allow liquid water. They can look at escape scenarios and ask whether an atmosphere could survive. They can study interior structure and density. In other words, the planet is not important because people want it to be special. It is important because the measurements are now good enough to trap the theory into a narrower space. And that is exactly when a planet becomes dangerous in a scientific sense. When the data are weak, everyone can keep their favourite idea alive. When the data improve, bad ideas start dying. TRAPPIST-1e keeps getting more interesting because it survives stronger constraints without becoming simple. It does not turn into an obvious dead rock. It does not turn into an obvious mini-Neptune. It stays in the narrow and uncomfortable zone where real models still disagree. That is why papers keep returning to it. It is one of the rare rocky planets where theory is being forced to answer to observation. Then the system gets even more serious, because the planets are not just close together. They are arranged in a linked orbital pattern that looks highly organised. TRAPPIST-1 is famous for its resonant architecture. The planets orbit in a chain where their timing ratios are connected in a structured way. This is not just a nice detail for orbital diagrams. Resonance gives scientists clues about how the system formed, how the planets moved through the original disk of gas and dust, and how the current arrangement was built over time. Later work even argued that the system likely formed in 2 steps, with the inner planets starting in a tighter resonance chain, before evolving into the pattern we see now. That matters because resonance is not decorative, it is evidence. It tells you the system probably did not form through random late chaos alone. It preserves memory of migration and assembly. It may also tell you something about how material moved through the disk and whether water and other volatiles were delivered inward or held back. So when scientists study TRAPPIST-1e, they are not only studying its present-day orbit, they are using orbital structure as a clue to the planet's past. The timing pattern becomes a kind of fossil record. It records how the system settled into its current form, and that history may still control whether the planet had the right ingredients to become habitable. This is where the whole subject stops sounding speculative. There is a real nearby star. There is a real resonance system around it. There is a real rocky planet in the system's most important habitable zone slot. Its size is measured. Its orbit is measured. Its mass is constrained through gravitational interactions. Its density is consistent enough with a rocky world that serious climate and atmosphere work is justified. Independent lines of measurement keep pointing to the same broad conclusion. TRAPPIST-1e is not a fantasy planet created by wishful thinking. It is a real target with real stakes, and once you reach that point, every uncertainty becomes heavier. If the planet has no atmosphere, that matters. If it has a thin, heavy atmosphere, that matters. If it has managed to hold water, that matters. If it lost everything early, that matters too. The reason the debate is intense is not because the planet is vague. It is because the planet is measured well enough that the remaining unknowns now control the meaning of the whole system. This is not science fiction. This is a forensic reconstruction of a world we cannot see directly, using light, timing, gravity, and orbital structure to narrow down what kind of place it really is. And that is exactly where the tension should rise, because once the planet becomes this real, the next problem becomes much darker. The better we measure TRAPPIST-1e, the more the same conclusion keeps coming back. The planet is interesting enough to matter, but the star may be violent enough to ruin everything. The problem is not just whether TRAPPIST-1e is in the habitable zone. The problem is what kind of star controls that zone. TRAPPIST-1 is small, faint, and easy to underestimate if you only look at total brightness. But brightness is not the whole story. Observations with XMM Newton showed that this star is a relatively strong X-ray source. One study found that its X-ray output in the 0.1 to 2.4 kilo-electron-volt range sits in the range of the quiet Sun. Even though TRAPPIST-1 is vastly dimmer overall, that is a serious warning sign. A star does not need to be big to be physically harsh. It only needs to deliver enough high-energy radiation in the wrong place for a long enough time. That changes the tone of the whole system. When people hear ultra-cool dwarf, they often picture a weak star that should be gentle by default. That is not how this works. A star can be weak in visible light and still be dangerous in the kinds of radiation that matter for atmospheric survival. X-rays and other high-energy emissions do not just light up space. They interact with upper atmospheres. They heat them, ionize them, and over long periods they can help drive atmospheric escape. So the planets around TRAPPIST-1 are not just sitting near a dim star. They are sitting near a star that may be especially effective at damaging thin, protective layers of gas. That is why the radiation environment matters so much. Once you move from how much light does the planet get to what kind of radiation is hitting the planet over billions of years, the habitability question becomes much harder. A rocky planet can sit in the right temperature range and still lose the atmosphere that would actually make surface water possible. High-energy radiation can strip volatiles, alter chemistry, and slowly reduce a world that once looked promising. So habitability here is not a simple temperature question. It is a long survival test. Can the planet keep enough gas? Can it keep or replace water? Can the chemistry stay stable enough for long enough? Can the surface avoid becoming sterile even if the orbit looks favourable on paper? That does not mean every planet in the system is automatically doomed. That part matters too. Some escape models suggest that the outer TRAPPIST-1 planets can retain atmospheres over billion-year timescales. So this is not a clean story where radiation kills everything and we move on. The danger is exactly that the answer is not that simple. Some worlds may lose most of what they started with, some may hold on, some may depend on an initial water inventory, outgassing, magnetic effects, atmospheric composition, or the exact history of the star's activity. That is why TRAPPIST-1e is such a loaded target. It sits in the zone where the fight between atmospheric loss and atmospheric survival becomes scientifically meaningful. And that is the right word for it, a fight. Around this star, habitability is not a stable background condition. It is a balance between erosion and recovery, between escape and replenishment, between harsh stellar forcing and whatever planetary mechanisms might push back. If TRAPPIST-1e has any meaningful atmosphere left today, then it may have held on to it through a very long period of stress. If it does not, that failure would also tell us something big. Either outcome matters because the system is old enough that short-term explanations are no longer enough. Then the story gets even more frustrating because the star is not only dangerous to the planet, it is dangerous to the measurements. This is the part people usually do not expect. You would think the hard part is just finding out what is physically happening on the world. But even reading the data is difficult because the star itself interferes. Star spots, flares, and magnetic surface features can distort transmission spectra. They can make a real atmospheric signal look weaker. They can imitate features that are not really from the planet. They can change from one observation to the next and turn a clean interpretation into a moving target. So the same star that may be stripping atmospheres is also making it harder to tell whether an atmosphere is there. That is not a small technical issue. It is one of the central reasons the TRAPPIST-1e story remains unresolved. Webb's work on this planet ran straight into the stellar contamination problem. Instead of a clean answer, researchers found that the star's behaviour was affecting the spectra strongly enough that separating the planet from the star became part of the main challenge. NASA's own public explainers have emphasised that TRAPPIST-1's activity has been more intense than expected, and that more observations than originally planned will be needed. That is a major point. The obstacle is not just weak instrumentation. The obstacle is that the target comes attached to a difficult star that keeps injecting noise into the evidence. That makes the uncertainty feel much more serious. People expect a more powerful telescope to remove doubt. They expect the next generation of instruments to take a blurry problem and turn it into a clean answer. But with TRAPPIST-1e, the opposite happened. The best telescope humanity has ever launched looked at one of the best rocky exoplanet targets ever found, and the result was not clarity. The result was a stronger confirmation of how hard the problem really is. The star complicates the measurements so much that even a world this important may require an extreme number of observations before scientists can speak with real confidence. That is why lines like hundreds of transits land so hard. NASA has said that potentially hundreds of transits over several years may be needed to characterize planets in this system with confidence. Think about what that means in practical terms. The signal is there, but it is buried. The target is nearby by exoplanet standards, but the answer is still expensive. The world is small, the star is active, the atmospheric signatures are subtle, and every observation has to fight through contamination. The uncertainty is not there because no one tried hard enough. It is there because nature set the problem up to be difficult. And once you see that clearly, the title starts to feel different again. TRAPPIST-1e is not unsettling because scientists found anything dramatic on the surface. It is unsettling because the parent star forces the planet into a narrow and unstable space between two huge possibilities. If a rocky planet can keep an atmosphere in this kind of environment, then red dwarf systems may be much more viable for habitability than many people once assumed. That would matter enormously because red dwarfs are the most common stars in the galaxy. A positive result here would not stay local. It would expand the map of plausible living worlds across a huge fraction of the Milky Way. But the opposite result would also be huge. If TRAPPIST-1e cannot hold on to enough atmosphere under a star like this, then one of the galaxy's most common planetary neighbourhoods may be far less friendly than planet counts alone suggest. That would push the search for life in a very different direction. It would mean that finding rocky planets in the habitable zone of red dwarfs is not enough. You would have to ask a much harder question every time. Did the star leave anything worth calling habitable after billions of years? That is why the star is the villain in this story. It sets the habitable zone, damages the planets, contaminates the data, and turns every answer into a harder question. It is the reason the system is so valuable observationally, and the reason the science remains so difficult. It gives astronomers access to small rocky planets and then fights them at every stage of interpretation. The line between life-friendly and life-erasing is not broad here. It is thin, and the star controls almost all of it. And that makes the next question even more important. If the star is this hostile, why does one planet in this system still keep drawing more attention than the others? Why does TRAPPIST-1e keep ending up in the centre of the case? The important question is not whether TRAPPIST-1e is in the habitable zone. The important question is why this planet keeps rising above the others in the same system. Habitable zone sounds simple, but it is not a guarantee, and it is not an equal label. Two planets can both sit near that zone and still have completely different outcomes. One can be pushed too far inward and start heading toward a runaway greenhouse state. Another can sit too far outward and need so much warming that the whole case starts sounding forced. TRAPPIST-1e keeps standing out because it sits in the narrow middle, where the models stop sounding desperate and start sounding realistic. That is the basic reason everyone cares about it. The inner planets are under stronger pressure from the star and are easier to picture as overheated. The outer planets may be easier to picture as frozen unless they get enough greenhouse support. TRAPPIST-1e keeps showing up in study after study as the world that is not obviously too hot, not obviously too cold, not automatically destroyed by tidal heating, and not so far from the star that warming becomes a stretch. In plain terms, if you are forced to choose one planet in this system as the best serious candidate for long-term surface habitability, this is the one that keeps winning. And it is not winning because scientists are trying to force a favourite. It is winning because the energy balance lands in the most interesting place. TRAPPIST-1e gets about 0.66 times the stellar flux Earth gets from the Sun. That number is close enough to matter, and not so low that you immediately give up. It puts the planet in a range where moderate greenhouse effects can plausibly make a real difference. That is exactly the kind of setup researchers want, because it means habitability does not depend on an absurd atmosphere or a heroic set of assumptions. The planet does not need to be rescued by extreme conditions. It only needs conditions that are serious enough to stay on the table. That is why the climate modelling on TRAPPIST-1e has carried so much weight. In 3D climate work, Wolf found that the planet could keep at least some habitable surface area with about 0 to 2 bar of carbon dioxide, depending on how much background nitrogen is present. Under some specific atmospheric mixes, the modelled temperatures can even move toward near-Earth values. That is a very careful statement, and that is exactly why it hits so hard. It does not claim the planet is a second Earth. It does not claim oceans have been found. It says something much more important. Under realistic atmospheric assumptions, this world can remain physically plausible as a place with liquid water conditions at the surface. That is enough to make the whole planet much more serious. Because once a world reaches the point where moderate atmospheric scenarios can support surface habitability, it stops being a remote curiosity. It becomes a real target for atmosphere question, water question, climate question, and long-term survival questions. The case becomes stronger because the required conditions are not ridiculous. You are no longer saying, maybe if everything goes exactly right. You're saying, under some reasonable conditions, this could work. Then there is the density theory, which makes it even harder to dismiss the planet. TRAPPIST-1e does not look like a puffed-up gas-rich world pretending to be rocky. Earlier density studies already pointed to it as one of the best candidates in the system for a largely rocky interior. Later work found that the 7 planets have remarkably similar densities overall, which matters because it supports the idea that these are compact terrestrial-type worlds, not hidden mini-Neptunes dressed up as something more exciting. For the video, the key point is simple. TRAPPIST-1e looks like the kind of planet where surface conditions are a legitimate scientific question. That is a major threshold. Before that threshold, the conversation stays vague. Once a planet looks compact and rocky, every atmospheric scenario becomes more immediate. The question is no longer whether the world is mostly gas. The question becomes whether it has air, what kind of air it has, how stable that air is, whether water can exist under it, and how the star has affected it over time. That is why TRAPPIST-1e keeps getting special attention. It is one of the few exoplanets where the basic physical picture is strong enough that surface and atmospheric questions are not fantasy anymore. Then there is another twist that makes the planet even more interesting. Tidal heating sounds like bad news, and sometimes it is. If a planet is constantly stretched and flexed by gravity, that can add internal heat and potentially push climate conditions in the wrong direction. But in this system, tidal effects are not automatically planet killers. That is one of the most counterintuitive parts of the whole story. Studies on TRAPPIST-1d and e found that they can avoid runaway greenhouse outcomes, and Planet E kept emerging as the most likely world in the system to support a habitable environment. So the same gravitational stress that can damage a planet can also help keep it geologically active and climatically complex. That matters because a completely dead interior is not ideal either. Internal activity can help drive out gassing, maintain cycles that affect the atmosphere, and keep a planet from becoming too static. So in TRAPPIST-1e's case, tidal effects are part of the tension, not an automatic disqualification. Too much heating can hurt, some heating can help, and that is exactly the kind of narrow balance that makes the planet such a powerful test case. It sits in a regime where several normally threatening factors do not simply cancel habitability, they interact with it. That is really the larger pattern here. Almost every major feature of the system can be read two ways. The close orbit is dangerous, but not automatically fatal. Tidal locking sounds severe, but may still allow stable habitable regions. Tidal heating sounds destructive, but may support useful internal activity. The red dwarf radiation environment is harsh, but not necessarily strong enough to erase every atmosphere in every case. And TRAPPIST-1e is the one planet where all of those competing effects seem to meet in the most interesting balance point. That is why this is not just one exoplanet story anymore. TRAPPIST-1e is a live stress test for the entire red dwarf habitability debate. If this planet turns out to be barren, that result will not stay local to one star system. It will affect how scientists think about rocky planets around M-dwarfs everywhere. It will strengthen the idea that being in the habitable zone is not enough when the host star is this active and the environment this difficult. But if TRAPPIST-1e turns out to have a stable heavy atmosphere, then the implications go the other way just as strongly. It would mean that the most common stars in the galaxy may support far more viable rocky worlds than the cautious view is willing to allow, and that is why this one planet carries so much weight. You're not just asking whether one distant rocky world can hold on to air. You're asking whether the dominant type of stellar real estate in the Milky Way may contain a much larger population of serious habitable world candidates than we were comfortable assuming. A positive result here would widen the map of plausible living worlds across the galaxy. A negative result would narrow it sharply. Either way, the answer does not stay on TRAPPIST-1e. That is also why the next step in the story matters so much. Before Webb pushed deeper into the system, another telescope had already started cutting options away. And what Hubble ruled out first turns out to be one of the most important reasons this planet stayed scientifically dangerous. The first major answer in this story did not come from Webb. It came from Hubble, and it removed one of the easiest possibilities before the main investigation even began. Hubble looked at several TRAPPIST-1 planets in and near the habitable zone range, and found that at least planet D, E and F do not appear to have big hydrogen-rich atmospheres like Neptune. That may sound like a small technical result, but it changed the entire direction of the science. It meant these worlds were not inflated gas-heavy planets pretending to be more interesting than they were. It meant one of the simplest explanations was already gone. That matters because a hydrogen-rich atmosphere is much easier to detect than the kinds of atmospheres scientists actually care about for habitability. A big light atmosphere spreads out more, blocks more starlight during a transit, and leaves stronger spectral signals. In plain language, it is the loud version. If TRAPPIST-1e had a puffy hydrogen envelope, the atmosphere question would have been easier from the start. The signals would be larger, the interpretation would be less subtle, and the whole system would be a cleaner target. But Hubble took that easy path away early, and once that happened, the story got harder in exactly the way that makes TRAPPIST-1e more important. The remaining possibilities were no longer simple gas-dominated worlds. They were much tougher cases. A thin, heavy atmosphere, a cloudy, heavy atmosphere, a denser secondary atmosphere, or no atmosphere at all. That is a much more difficult scientific problem, because those cases produce smaller signals and leave more room for ambiguity. So Hubble did not make the system less interesting. It made it much more serious. It turned the job from broad classification into precision testing. That shift is a huge part of the drama. Before Hubble's result, the question could have gone in a simpler direction. Scientists could have found out that these planets were wrapped in hydrogen-rich atmospheres and moved on from the more exciting surface habitability discussion. That would have been useful, but it would have lowered the stakes. Instead, Hubble forced the opposite outcome. It showed that at least some of the planets were not in the easy category. That pushed TRAPPIST-1e deeper into the narrow zone, where the atmosphere could still matter for surface conditions, but where proving anything would become much harder. That is why this result was so valuable. It killed a whole class of worlds in one move. It did not prove TRAPPIST-1e had a habitable atmosphere. It did not prove it had any atmosphere at all. But it removed the broad, bloated hydrogen explanation that would have made the planet much less relevant to the life question. Once Hubble ruled that out, the surviving scenarios became much more aligned with the kind of rocky world people actually care about. The planet stopped being a simple atmospheric detection target and became a hard atmospheric interpretation target. And that difference matters. Detection alone is not the same as understanding. A hydrogen-rich atmosphere is almost too easy from a signal standpoint. The scale height is larger, the features are bigger, and the telescope has more to work with. When that option disappears, the problem changes immediately. Now you're looking for smaller signatures from heavier gases. You're dealing with clouds that can flatten spectra. You're dealing with atmospheres that may exist but barely reveal themselves. Or you are dealing with bare rock, which can look frustratingly similar in limited data. The signal gets smaller, the uncertainty gets sharper, and every observation matters more. That is why Hubble effectively changed Webb's mission before Webb even started looking closely at TRAPPIST-1e. NASA described the Hubble observations as early reconnaissance for Webb, and that is the right way to think about it. Hubble did not finish the case. It narrowed the battlefield. It said the broad, "Is this a puffy gas world?" question was already mostly out of the way for key planets. So when Webb entered the story, it was not arriving as a wide survey tool asking basic first-round questions. It was arriving for a much harder assignment. It had to test whether TRAPPIST-1e has a thin, heavy atmosphere, a cloudy, heavy atmosphere, some other compact secondary atmosphere, or nothing at all. That is a much more brutal problem, but also a much more meaningful one. If the answer had stayed in the hydrogen-rich category, the habitability discussion would have been weaker. But once the system moved into the high molecular weight or no atmosphere range, every new observation became more important to the larger question of whether a rocky red dwarf world can actually hold on to the kind of atmosphere that matters for liquid water and long-term climate stability. So Hubble did not just prepare Webb technically, it prepared Webb scientifically by making the target harder and more valuable at the same time. And this was not only about Planet E. The system-wide implication was already becoming clear. By 2020, review work that pulled together the Hubble transit data, the density measurements, escape modelling and gas accretion arguments was already pointing toward a strong conclusion. The TRAPPIST-1 planets did not look like hydrogen-dominated worlds. That kind of synthesis matters because it is not based on one single clue. It is built from multiple lines of evidence that all push in the same general direction. The broad, easy answer kept disappearing from more than one angle. That is the kind of result that changes the tone of the whole system. Once the planets probably either have high molecular weight atmospheres or no atmospheres at all, there is much less room for comfortable middle ground thinking. You are no longer dealing with a wide menu of broad possibilities. The options narrow into harder categories. Either these rocky worlds kept more compact, denser atmospheres under a difficult star, or many of them lost almost everything. And that split is exactly what makes the TRAPPIST-1 system so powerful. It is not just a set of 7 planets. It is a comparative test of atmospheric survival under one star. For TRAPPIST-1e specifically, this sharpened the stakes. If the planet ever developed life-friendly conditions, it was not going to do it with a huge easy-to-detect hydrogen blanket. That road was already fading. The more realistic paths were tougher from the start. A secondary atmosphere, a heavier atmosphere, something denser, lower in scale height, harder to read and more vulnerable to long-term erosion. Or no atmosphere at all. That means even the optimistic scenario is not soft. Even the hopeful version of this story still involves a rocky world trying to keep a difficult atmosphere under a difficult star for billions of years. And that is why Hubble's result sounds modest but hits so hard once you understand it. It did not announce life. It did not announce oceans. It did not even announce a confirmed atmosphere. It simply removed the easy answer. And once the easy answer dies, the remaining possibilities become much more unsettling. Because if TRAPPIST-1e is still interesting after hydrogen-rich atmospheres are ruled out, then it is interesting in the most serious way possible. It means the planet's future in the habitability debate depends on the existence of a much subtler, much harder to detect kind of atmosphere that would have had to survive real punishment. That is what makes the title feel more menacing, not less. If life ever did emerge on TRAPPIST-1e, it would not have had a comfortable oversized atmosphere helping it along. It would have had to exist on a compact rocky world under a harsher atmospheric regime, under weaker signals, under stronger uncertainty, and possibly after billions of years of erosion pressure from the star. So even the optimistic path through this system is narrow. Even the hopeful version is demanding. And that sets up the next section perfectly, because once Hubble killed the easy case, Webb had to face the harder one directly. And when Webb finally looked at TRAPPIST-1e, the result was not a clean victory. It was something much more frustrating. This is the point where people expect the story to become simple. Webb shows up, looks at one of the best rocky planets we have, and gives a clear answer. That is not what happened. In 2025, teams released the first 4 JWST NIR spec transmission spectra of TRAPPIST-1e, based on transits collected in 2023 through the DREAMS collaboration. On paper, that sounds like the moment the fog should clear. 4 transits! One of the most powerful telescopes ever built. One of the most important rocky exoplanets in the sky. But the result was not a clean win. The spectra showed strong stellar contamination, and it changed from one visit to the next. That point matters immediately. The planet was not giving a stable, clean signal that scientists could just read off like a label. The star kept interfering. The contamination was not just present, it was variable. That means the background problem was moving during the experiment. And once that happens, every interpretation becomes harder. A weird feature in the spectrum might be from the planet, or it might be from the star. A flat result might mean no atmosphere, or it might mean the atmosphere is being hidden by stellar effects and noise. So even with Webb, the first serious answer was not clarity. It was proof that the star was still controlling the fight. That is a big deal because Webb was supposed to push the question into a new phase. Hubble had already helped remove the easy hydrogen-rich path for the system. Webb was supposed to go deeper and test the harder cases. It did do that, but not in a satisfying, clean way. It squeezed the options further without collapsing them into one answer. That is why these 2025 papers matter so much. They did not settle the case. They made the shape of the problem much sharper. One of the clearest results was another hit against thick hydrogen atmospheres. One paper reported that the transmission spectra could rule out cloudy primary hydrogen-dominated atmospheres above about 80% hydrogen by volume at better than 3 sigma. That is not a small technical detail. That is Webb taking the older Hubble result and pressing harder on it with stronger data. It means TRAPPIST-1e is not behaving like a world that held onto a big primordial hydrogen envelope. The planet does not look like a small version of a gas-rich world with a light-inflated atmosphere. That route keeps closing. And that matters because every time the hydrogen-rich option takes another hit, the remaining cases become more serious. If there is an atmosphere there, it is much more likely to be secondary, heavier, and closer to Earth-like in mean molecular weight than to a mini-Neptune envelope. That does not mean Earth-like in climate or comfort. It means denser molecules, smaller scale height, weaker spectral signals, and a much harder detection problem. In other words, Webb did not tell us the planet is easy to understand. It told us the easy version is becoming even less likely. But this is where the tension gets stronger instead of weaker. The atmosphere did not disappear from the case just because thick hydrogen took another loss. The companion analysis made that very clear. The team said they found no strong evidence either for or against an atmosphere. That is the sentence people often miss, and it is the most important one in the whole section. No strong evidence for, no strong evidence against. After years of anticipation and some of the best data ever taken for a rocky exoplanet, the planet still sits between major possibilities. The same analysis weakly disfavored carbon dioxide-rich atmospheres at pressures corresponding to Venus and Mars' surface pressures and Venus's cloud tops at about 2 sigma. That is useful, but it is not a final elimination. More importantly, they found that nitrogen-rich atmospheres with trace carbon dioxide and methane were still allowed by the data. And a bare rock also still fit the observations. That is the part that should really land. The current answer still stretches all the way from airless stone to a heavy secondary atmosphere that remains difficult to detect. That is not a failure of science. That is the exact shape of the frontier. When the surviving options are that far apart, it means the target is balanced right at the edge of what current measurements can separate cleanly. The instruments are powerful enough to rule out some worlds, but not yet powerful enough to finish the job. So TRAPPIST-1e remains trapped in one of the most uncomfortable positions possible. It is too constrained to be fantasy and too ambiguous to be settled. And that is why the 2025 results feel so intense. They are not dramatic in the cheap way. There was no Webb found life headline. There was no Webb proves the planet is dead headline either. Instead, the telescope delivered something more difficult. A narrowing of the plausible worlds without a final identification of which world this actually is. That is much harder to package, but scientifically it is much bigger. It means we are now comparing serious atmospheric scenarios against real high-quality data, and still finding that multiple radically different outcomes survive. NASA's public summary in September 2025 captured that balance in a very careful way. The message was that Webb had found no definitive signs of an atmosphere around any of the 4 inner TRAPPIST-1 planets observed so far, including E, that is the public-facing caution. But the same summary also made clear that TRAPPIST-1e remained a major target and that 15 additional observations were already underway. That combination tells you everything about the real scientific mood. The answer is cautious in public because the evidence has to be treated honestly. The commitment behind the scenes is enormous because the target is still worth the price. That point should not be missed. Scientists do not keep spending that much Webb time on a dead lead. They do not keep pushing specialized observing programs at a world that has already stopped mattering. 15 more observations is not routine curiosity. It is a sign that the field understands how important the distinction is. A bare rock and a thin, heavy atmosphere are not minor variants of the same result. They point to completely different realities for red dwarf habitability. If TRAPPIST-1e is airless, that is one message about survival near small active stars. If it has a stable secondary atmosphere, that is another message entirely. And there is one more reason these results matter so much. The ambiguity is not random. It is not coming from sloppy work or weak interest. It is coming from the fact that the signal separating the possibilities is tiny, and the host star is making the measurement harder at every stage. That changes the emotional weight of the story. The answer is not missing because nobody has looked carefully enough. The answer is difficult because one of the best rocky planets we know is orbiting one of the most annoying stars it could possibly orbit for this kind of science. So Webb did not tell us there is life on TRAPPIST-1e. It told us something much more unsettling. On one of the best rocky planets we have ever found, the universe is forcing us to choose between multiple very different realities while making the line between them extremely hard to read. A bare rock still works. A heavy secondary atmosphere still works. Some carbon dioxide-rich cases look weaker. Thick hydrogen looks increasingly unlikely. The possibilities are shrinking, but they have not collapsed. That is why this section matters so much to the whole story. Webb did not remove the mystery. It upgraded it. It turned TRAPPIST-1e from a promising target into a precision problem at the edge of current exoplanet science. And once the thick hydrogen option keeps fading, the next question becomes even more important. If a big, easy atmosphere is not there, then the most unsettling possibility is not a giant obvious world. It is a thin survivor atmosphere that held on anyway. The easiest answer is starting to look wrong, and that makes the harder answer much more disturbing. A thick hydrogen atmosphere would have been simple to understand. A bare rock is simple too. Those are clean outcomes. Either the planet kept a big light atmosphere, or it lost almost everything and ended up exposed. But the middle case is the one that really changes the story. A thin, high molecular weight secondary atmosphere that survived around this star for the billions of years is much harder to prove and much harder to ignore. Because if that is what TRAPPIST-1e has, then this is not a puffed up mistake and not a failed world. It is a compact rocky planet that found a narrow way to stay in the game under conditions that should have made that difficult. That is why this possibility feels heavier than the others. A hydrogen-rich atmosphere would tell you the world kept something big and obvious from early formation. That would be useful, but it would not tell you much about true Earth-class survival. A bare rock would also be a clear answer. It would say the star won. But a thin survivor atmosphere says something much more important. It says a rocky planet close to a violent red dwarf may be able to lose the easy stuff, avoid becoming a gas-heavy world, and still hold on to enough of the right kind of air to matter. That is the outcome that really threatens old assumptions, and this is not just a dramatic guess. The 2025 retrieval work left that door open very clearly. The analyses said nitrogen-rich atmospheres with trace carbon dioxide and methane are still compatible with the data. That line matters a lot, because nitrogen does not make itself easy to see. It is not a loud gas in transmission spectroscopy. It does not produce the kind of huge, obvious signature that lets a telescope settle the question quickly. So the atmosphere that may be most relevant for surface habitability could also be one of the hardest to detect directly. That changes the tone of the whole search. People often assume that if a planet is important enough, the evidence will eventually be dramatic and obvious. But nature does not promise that. On a world like TRAPPIST-1e, the atmosphere that matters most may be quiet. It may leave only weak fingerprints. It may hide behind a nearly flat spectrum. It may exist in a form that is physically meaningful but observationally frustrating. That means the universe may not be hiding the most important worlds behind giant signals. It may be hiding them behind chemistry that barely announces itself. And once you accept that, the next point gets even more intense. TRAPPIST-1e may not need extreme conditions to stay relevant. That is what makes the survivor atmosphere idea so uncomfortable. Multiple climate studies have shown that this planet does not require absurd rescue scenarios to remain interesting. It does not need a giant atmosphere. It does not need a completely unrealistic greenhouse blanket. Moderate greenhouse support can move it towards stable liquid water conditions. Wolf's 3D climate work showed habitable surface area under modest carbon dioxide inventories, and later studies have kept Planet E in the most favourable position in the system. That is a very serious implication. The disturbing part is not that TRAPPIST-1e might be some perfect paradise. The disturbing part is that it may not need to be. It may only need a limited atmospheric foothold. It may only need enough pressure, enough heat transport, enough greenhouse support, and enough retained volatiles to keep part of the surface or near-surface environment stable for long periods. That is a smaller demand than most people expect when they hear the word habitable. And smaller demands mean more worlds stay in play. That is where the whole Earth 2.0 idea starts to break down. TRAPPIST-1e does not need to become a second Earth to matter. In fact, thinking that way may block the real point. This planet may have permanent day on one side and permanent night on the other. It may have strong atmospheric circulation moving heat between those sides. It may have limited regions where liquid water is stable instead of a globally comfortable surface. It may live under a heavy or semi-heavy atmosphere that does not resemble Earth's balance very closely. It may deal with a level of stellar forcing that would sound extreme if you described it without context. And still, if chemistry can stay organised long enough in some persistent, stable region, then in the only important sense, the planet could still count as habitable. That is the shift this world keeps forcing. The real standard is not whether it looks familiar. The real standard is whether it can maintain conditions that let complex chemistry keep going instead of breaking apart. That is a much broader and more difficult idea than the public version of habitability. It means a planet can be strange, uneven, harsh, and still physically capable of supporting life. It means the template may never have been a lot like Earth. The template may be stable enough for long enough, even if the environment looks alien by human standards. And if that is true, then the implications go far beyond TRAPPIST-1e itself. A survivor atmosphere on this planet would mean the galaxy may contain many more borderline worlds than people expected. Not obvious blue marble planets, not worlds that announce themselves with perfect biosignatures and easy spectra. Borderline worlds, narrow survival worlds, worlds that hold on to just enough atmosphere to matter, just enough water to stay active, just enough climate stability to avoid complete collapse. Those planets would be much harder to notice, much harder to confirm, and much easier to underestimate. That possibility is more unsettling than the older, simpler version of the search for life. The old picture is clean. You look for planets that resemble Earth, orbit calm stars, and show strong atmospheric signals. The new picture is much less comfortable. You may be looking for worlds that do not look ideal at all. Worlds around red dwarfs. Worlds with strange circulation patterns. Worlds whose spectra look almost flat. Worlds that seem nearly dead until you study them closely enough to realize they are not fully dead and not fully easy either. That is a stranger universe, because it means life-friendly conditions may exist in forms that do not advertise themselves. And that is why the survivor atmosphere scenario feels so important. It does not just keep TRAPPIST-1e in the discussion, it changes the meaning of the discussion. If this planet has a thin, heavy atmosphere that survived, then the lesson is not, we found another Earth. The lesson is that Earth may be only one version of a much wider set of viable worlds. A red dwarf planet with difficult light, difficult climate patterns, difficult data, and only partial habitability could still count. That would force astronomy to widen its idea of where life might persist. It would also make the silence of the data feel very different. A flat or weak spectrum would no longer mean nothing is happening there by default. It could mean the exact opposite. It could mean the atmosphere is subtle, compact and hard to separate from the star. It could mean the world is physically active but observationally quiet. It could mean one of the most important classes of habitable planets in the galaxy is also one of the hardest to prove. That is a serious warning for the future of the field. The planets that matter most may not be the ones that make the biggest signals. So the fear here is not just scientific, it changes the whole picture of the galaxy. A survivor atmosphere on TRAPPIST-1e would mean life-friendly planets may not show up as obvious success stories. They may sit around red dwarfs with weak spectral fingerprints, harsh conditions, and just enough stability to stay relevant. They may look disappointing until the data get good enough. They may be easy to overlook and hard to confirm, and if that is true, then the galaxy could be full of worlds doing the minimum required to stay alive while looking almost silent to us. That is a much stranger universe than the old one. Not because it is full of obvious inhabited planets, but because it may be full of worlds balanced right above failure. Worlds that do not look welcoming, do not look dramatic, and do not give up their secrets easily. TRAPPIST-1e matters because it may be one of the first real tests of that possibility. And once you start thinking that way, the next common assumption also starts to collapse. Because people hear tidally locked and think the case is over. But for this planet, even that may not mean what they think it means. A lot of people hear tidally locked and think the case is over. One side always faces the star, one side stays in darkness forever. So the day side must burn and the night side must freeze. That sounds simple, it sounds fatal, but for TRAPPIST-1e that picture is too crude. Yes, the planet is so close to its star that synchronous rotation is the expected outcome. That means permanent day on one hemisphere and permanent night on the other. But that does not automatically turn the planet into a dead split world. Once you include an atmosphere, clouds and heat transport, the situation changes fast. That is the first thing that needs to be corrected. Tidal locking is a serious condition, but it is not a final verdict. It tells you the planet has a very unusual climate setup. It does not tell you that habitability is impossible. A world with permanent day and permanent night can still move heat through the atmosphere. Winds can carry energy away from the hot side. Clouds can reflect incoming light and cool the day side. The night side can stay warmer than people expect if the atmosphere is doing enough work. So the standard pop science version is not completely wrong, but it is incomplete in the exact way that matters most. And once you move past that oversimplified picture, the most interesting part of the planet is not the whole surface. It is the specific region directly under the star. That substellar point is where the climate models become much more important than the intuition. Turbot and colleagues argued that if TRAPPIST-1e is synchronously rotating and rich in water, it should very likely maintain surface liquid water at least in the substellar region, whatever atmosphere is considered. That is a major result, because it breaks the most common assumption cleanly. You do not need an Earth-like planet with oceans spread across the globe to get a stable zone where liquid water can exist. That changes the whole shape of the discussion. The question stops being, is this world globally comfortable? And becomes, can this world maintain a stable hydrological niche somewhere on the surface? That is a much harder and much more interesting question. A planet can be strongly asymmetric and still be relevant. It can have one region under constant starlight where conditions are stable enough for liquid water, while other regions are much harsher. That means habitability may come in patches, not planetary averages. And once that idea enters the story, the old standard starts breaking again. A world does not need to look balanced from space to matter biologically. That does not mean the risks go away, they just become more specific. One of the real dangers on a synchronously rotating planet is atmospheric collapse on the night side. If certain gases get too cold, they can freeze out. Carbon dioxide is the classic example people worry about. If enough of it condenses on the permanent night side, the atmosphere can become unstable or collapse into a much less useful state. That sounds catastrophic, and in some planetary setups it absolutely is. So this is not a place where the science becomes optimistic and simple. The danger is real, but again, TRAPPIST-1e is not a clean failure case. The climate work does not say the planet is doomed to night-side collapse by default. In fact, studies on the TRAPPIST-1 system found that with around 1 bar of nitrogen, TRAPPIST-1e and f should be protected against carbon dioxide atmospheric collapse. That is a very important point. It means the atmosphere does not need to be absurdly thick to matter. A plausible background gas inventory can be enough to support pressure and heat transport strongly enough to keep the climate from falling apart in that way. So the same tidal locking setup that sounds fatal in the simplified version becomes much more conditional in the real modelling. That is exactly why this planet keeps getting attention. Every threatening feature in the system turns out to be real, but not automatically decisive. Tidal locking is real. Nightside collapse is a real risk. Strong day-night contrast is real. But none of those facts by themselves are enough to remove TRAPPIST-1e from the serious habitability conversation. The outcome depends on the atmosphere, the heat transport, the pressure, the cloud response, and the water inventory. That makes the world more difficult, but also much more important scientifically. And this is not some niche argument built on one model. TRAPPIST-1e became important enough that researchers built an entire model inter-comparison effort around it. The TIE project exists because one climate model was not enough for a planet like this. In the simulated observables work from that project, 4 different global climate models were compared. For aquaplanet cases, the predicted number of transits needed for atmospheric detection could be at least 17, and cloud differences alone introduced about 35 to 40% uncertainty. That is not a minor detail. That is the field openly showing how seriously it takes this planet, and how hard it is trying to separate robust conclusions from model-specific assumptions. That point matters because it tells you this is not fringe speculation. Scientists do not build multi-model comparisons around a planet unless the target is important and the problem is genuinely difficult. TRAPPIST-1e forced the community to ask not just what does one model say, but what survives across several different climate models. That is a much higher standard. And even at that standard, the planet stayed interesting. The uncertainties are large, but they are structured uncertainties, not chaos. The modelers are arguing over cloud behavior, circulation efficiency, and observational consequences, not over whether the whole topic is nonsense. So when people say a tidally locked world sounds too extreme to matter, they're behind where the science already is. The current question is not whether a synchronously rotating rocky planet can have a climate. The question is what kind of climate it has, how stable that climate is, how detectable it is, and whether any part of that climate can maintain liquid water over long periods. That is a much more advanced and much more serious discussion. And TRAPPIST-1e is one of the main planets pushing it forward. This is also where the meaning of Earth-like has to change again. TRAPPIST-1e may never be Earth-like in the visual sense people instinctively prefer. It may have extreme day-night contrast. It may have cloud structures centered near the permanent day side. It may have circulation patterns that look nothing like Earth's. It may have no real analogue to the daily rhythm we take for granted. It may be alien in exactly the way movies almost never show, but none of that disqualifies it. If the atmosphere moves energy well enough, if some region stays wet enough, and if chemistry can remain organized there long enough, then the old visual standard stops mattering. That is the deeper point of this section. A habitable world does not need to be a planetary copy of Earth. It may be a climate mosaic. It may be a world where stability exists only in certain regions. It may be a world where one part of the surface does most of the biological work, while the rest is much less forgiving. That is still habitability, and once you accept that, the search for life gets much wider and much stranger. You're no longer looking only for planets that feel familiar. You are looking for planets that can maintain the right physical and chemical conditions somewhere, somehow, despite having a global setup that feels extreme. That is why tidal locking does not kill the TRAPPIST-1e story. It actually makes the story sharper. It forces the science to ask what kind of stability matters, how local that stability can be, and how strange a living world is allowed to look before we stop recognizing it as possible. TRAPPIST-1e may not be a global ocean world with mild weather and a balanced day-night cycle. It may be something much harder to picture and much harder to detect. But if one region can stay stable enough for water and chemistry to persist, then the old habitability picture is no longer big enough. And once that sinks in, the next question becomes unavoidable. Even if the climate can work in pieces, even if the atmosphere can move heat, even if the night side does not automatically destroy the planet, there is still one resource that has to survive all of this: water. And around a red dwarf, water is not just part of the story, it is the war. The next problem is bigger than atmosphere by itself. The real fight is over water. Around ultra-cool dwarfs like TRAPPIST-1, Water is not something you assume is present just because a planet sits in the habitable zone today. Early in the life of these stars, the radiation environment can be much more punishing than people expect. High-energy radiation can drive atmospheric escape, break apart water molecules, and over long periods help remove huge amounts of water from nearby planets. So when scientists study TRAPPIST-1e, they are not only asking whether the planet could support liquid water now, they are asking whether enough water could have survived the star's history for that question to still matter. That is why the water story has to be treated as a long emergency, not a simple starting condition. A planet can begin with water and still lose too much of it. A planet can begin with a decent atmosphere and still have that atmosphere changed by escape over time. Around a star like TRAPPIST-1, habitability is not just about whether the orbit is in the right range today. It is about whether the planet got through billions of years without having its useful volatiles stripped away. Boltzmann's work made this point clearly by treating the TRAPPIST-1 planets as key targets for understanding water erosion around ultra-cool dwarves. Later escape models added to that picture by showing that the outcome depends on more than one factor. Initial water inventory matters, the exact planet-star distance matters, the long activity history of the star matters, the composition of the atmosphere matters. In other words, water here is not a background ingredient. It is something the planet may have had to fight to keep. That is also why the X-ray issue matters so much. Earlier, the star's X-ray brightness sounded like a warning sign in general terms. Here, it becomes much more concrete. The XMM Newton study was not just cataloguing stellar activity for its own sake. It was explicitly asking what that activity means for the possible oceans and atmospheres on the planets. That gives the whole question a very different weight. The issue is probably not whether TRAPPIST-1e ever had water at all. The issue is whether, after billions of years under a star capable of driving escape and long-term erosion, it could still hold on to enough water for a meaningful climate to survive. That is a much harder version of habitability. You're no longer asking whether the chemistry of water is possible on the planet. You're asking whether the planet could endure long enough, under enough stress, without losing too much of the resource that makes the entire conversation worth having. A planet can survive as a rock and still fail this test. A planet can survive with some atmosphere and still fail this test. Water is what raises the stakes because it connects the climate, the surface, the atmosphere, and the deep time history into one question. If too much of it is gone, the rest may not matter. But this is also the point where the story has to stay balanced. Not every serious paper ends with total desiccation. Some models do not describe a doomed system. Boltzmann's work said that depending on initial water contents, the planets could still have enough water to remain habitable. Dong and colleagues concluded that the outer planets can retain atmospheres over billion-year timescales. And once again, climate studies keep returning to TRAPPIST-1e as the planet most likely to sit in the favourable middle range, rather than at either extreme. So the scientific picture is not the star destroyed everything. The scientific picture is that water survival is now one of the most important open questions in the entire system. That distinction matters. A doomed planet is scientifically interesting, but only in one direction. A planet that may or may not have retained enough water is much more important, because the answer changes how we interpret a huge class of worlds around small stars. TRAPPIST-1e remains valuable because it may have threaded the needle. It may not have needed to keep all its original water. It may only have needed to keep enough. Enough for some climate stability, enough for regional liquid water, enough to maintain chemistry over long timescales. That is a much narrower requirement than ocean paradise, and that is exactly why it is so unsettling. The threshold for staying biologically relevant may be lower than people assume, and then there is a darker clue that comes from one of the neighbouring planets. Sometimes the best information about one world comes from the failure of another. In 2023, work on TRAPPIST-1c found no thick carbon dioxide-rich atmosphere there, and one interpretation of that result was that C may have formed with a relatively poor volatile inventory. The paper argued for less than about 9.5 Earth oceans of water for planet C. That is already important on its own, but the more uncomfortable point is the system-wide implication. If the TRAPPIST-1 planets formed in broadly similar ways, then a volatile poor history for C could mean the potentially habitable planets also started with a more limited supply than optimistic scenarios assumed. That is a serious warning, then, because it means TRAPPIST-1e's prospects may not be determined only by what happened to E after formation. They may also depend on what kind of starting conditions the whole system inherited. If the sibling planets are telling us that the system began with a restricted volatile budget, then TRAPPIST-1e may have had less room for error from the start. It may have entered its long fight with the star without a huge reserve, and if that is true, then every bit of atmosphere retained, every bit of water preserved, and every stabilizing climate effect becomes more important. This is what makes comparative planetology in TRAPPIST-1 so powerful. You are not reading one isolated world. You are reading a family of worlds under shared stellar conditions but different orbital positions. If one inner planet looks stripped, that tells you something about what the star can do. If another lacks a thick, volatile-rich atmosphere, that tells you something about formation or loss. If TRAPPIST-1e turns out to be the one that kept enough to matter, that would not just be a positive result for E. It would mean the difference between failure and survival in this system may come down to a very narrow band of initial conditions and long-term endurance. That is exactly the kind of result scientists care about because it is not just descriptive, it is explanatory, and that brings the emotional centre of the whole section into focus. The frightening possibility here is not that TRAPPIST-1e hosts some dramatic alien ecosystem. The more serious possibility is that this planet may have spent billions of years right on the edge, losing some water, holding on to some, collapsing some atmospheric pathways, rebuilding others, getting pushed by radiation, getting helped by climate feedbacks, maybe never becoming comfortable, but maybe never fully failing either. That is a very different image from the standard habitable world picture. It is not a calm world waiting to be discovered. It is a world that may have survived by doing just enough for just long enough. That is why water is the real war. Water is what turns TRAPPIST-1e from a promising target into a profound one. A rocky planet with the right temperature range is interesting. A rocky planet that may have preserved enough water to stay in the habitability conversation after billions of years around a difficult star is something else entirely. That is a direct test of whether life-friendly conditions can persist in places we once would have written off as too unstable, too stripped, or too hostile. And if the answer depends partly on the rest of the system, then the next step gets even more important. Because TRAPPIST-1e is not being judged alone. Its neighbouring planets are acting like comparison points, warning signs and reference cases all at once. And that means the rest of the system is not background. The rest of the system is part of the evidence. This system matters more because TRAPPIST-1e is not standing alone. It comes with siblings, and that changes everything. If this were one isolated planet around one isolated star, the uncertainty would be much harder to interpret. But that is not what we have. We have a family of rocky worlds around the same star, all exposed to the same general stellar personality, but sitting at different distances and in different climate regimes. That turns the whole system into a natural laboratory. You're not just asking what happened to one planet. You're asking how the same star treats a lineup of worlds under different conditions. That is what makes the suspense sharper. Planet B and C sit much closer in and take the worst of the irradiation. Planet D sits in a more uncertain middle zone. Planet E is the current main target because it keeps looking like the best compromise. Then F, G and H move outward toward colder possibilities. So every time one planet gives up a clue, that clue does not stay local. It changes how you read the others. If one inner planet looks stripped, that tells you something about the power of the star. If one outer planet hangs on to something, that tells you something about where the survival line may be. The planets are not just neighbours, they are reference points for each other. That is why the newer results on B and C matter so much. According to NASA's January 2026 explainer, Webb has not found signs of thick atmospheres on either TRAPPIST-1b or TRAPPIST-1c. The current data for B suggest it may be a bare rock, and if C has an atmosphere at all, it is likely very thin. That is a big result because it takes one of the major fears in this system and moves it out of the theoretical category. Close-in rocky planets around this star really can get stripped down brutally. This is not just a model warning anymore. There are now worlds in the same system that look like casualties. That changes the emotional balance of the whole story. It means the harsh radiation environment is not something people are worrying about in the abstract. We can already see planets in the lineup that appear to have lost the easy atmospheric battle. Planet B in particular becomes a very important object because it looks like the kind of world the star can reduce to near bare conditions. Once that is on the table, every question about E becomes heavier. You're no longer asking whether TRAPPIST-1 might be dangerous in principle. You're asking whether E somehow avoided the fate that seems to have hit some of its siblings. Then there is Planet D, which makes the middle ground even more uncomfortable. NASA's 2025 release on TRAPPIST-1d said Webb did not detect molecules like water, methane or carbon dioxide that would go along with an Earth-like atmosphere, and that the planet can be ruled out as an Earth twin or even an Earth cousin. That already closes one hopeful door, but the result still does not become simple. NASA also left open the possibilities of a thin Mars-like atmosphere, thick high clouds or no atmosphere at all. So even in disappointment, the system stays complicated. The planets are not falling into neat categories. They are mapping a gradient between retention and ruin. That is exactly why TRAPPIST-1e becomes more important, not less. When B looks stripped and C looks thin and D loses the Earth-like case, E starts to stand out more clearly as the planet sitting closest to the survival boundary people care about most. But at the same time, that also makes E feel more fragile, because now it is not being compared to optimism, it is being compared to losses. Every negative result on the inner planets raises the pressure on E. If E has an atmosphere, it may be one of the system's strongest examples of long-term survival. If it does not, then the pattern of failure becomes much harder to ignore. That is the trade-off NASA pointed to in the same D release, and it is one of the most important trade-offs in the whole story. The outer planets, including E, may have better chances of retaining atmospheres because they are farther from the star's strongest energetic eruptions. That is the hopeful part. But those same planets are also colder, and their atmospheric signatures are smaller and harder to detect. That is the frustrating part. So the place most likely to stay habitable is also one of the hardest places to read clearly. The answer is not being withheld by bad luck. It is being withheld by structure. The system is built in a way that makes the most important worlds the most difficult to interpret. That is why comparative planetology becomes part of the suspense instead of just background science. Every result in the system changes the odds somewhere else. If B is bare, that strengthens the case that the star can strip worlds down. If C is thin, that says atmosphere survival gets difficult fast as you move inward. If D loses the Earth-like option, but still keeps some ambiguity, that tells you the middle region is complicated rather than clean. And then E sits just far enough out to remain plausible while still being maddeningly unresolved. The family pattern makes E look both more promising and more precarious at the same time, and then the story adds one of its best twists. The planet that looks most damaged may help unlock the one that matters most. Scientists are now using TRAPPIST-1e, the likely airless inner planet, as a calibration tool when B and E transit in close sequence. The idea is clever because B is likely giving mostly the star's contamination signal without much atmospheric complication of its own. That makes it useful as a reference point. If you can use B to better understand what the star is doing, you can subtract that contamination more effectively when E transits and get a cleaner look at whether E has air. That is a very powerful detail because it turns the system's damage into part of the solution. The world that seems to have lost the atmospheric fight may become the tool that helps identify whether another world survived it. In a system this difficult, even the stripped planets are still useful. Even failure becomes data. That is one of the reasons TRAPPIST-1 is such a strong scientific target. It is not just one promising world surrounded by noise, it is a full comparative setup where each planet helps define the others. So when people focus only on TRAPPIST-1e, they miss part of what makes it so important. E matters because of what it is, but it also matters because of where it sits in this family. It is bracketed by worlds that already look harsher, thinner, or more obviously damaged. It sits in the slot where atmosphere retention might still work, but only barely. That makes every sibling result part of its case file. The inner planets are showing you what loss can look like. The outer planets show where survival might become easier but harder to detect. And E is right in the part of the system where the line between those outcomes may actually be measurable. That is why the neighbour worlds make TRAPPIST-1e more important. They turn one planet into a test with controls. They let scientists compare worlds under one stem rather than guessing from isolated examples. They make the system feel less like a set of separate discoveries and more like a coordinated experiment nature ran on its own. And right now, that experiment is pointing toward one uncomfortable idea. The difference between a bare rock and a potentially habitable world may be very narrow, very fragile, and very dependent on details we are only starting to extract. And even if TRAPPIST-1e does have air, there is another problem waiting right behind that. Because a gas in a spectrum is not always what people want it to be. Around a red dwarf, chemistry itself can mislead you. This is where the story gets even harder, because even a good atmospheric signal would not automatically mean life. Around red dwarfs, you cannot treat oxygen like a magic answer. A lot of people hear oxygen in an exoplanet atmosphere and think the case is basically solved. On Earth, oxygen is deeply tied to biology, so that reaction makes sense. But around M-dwarf stars, that shortcut can fail badly. A planet can build up a biotic oxygen or ozone through photochemistry and other non-biological processes. So even if TRAPPIST-1e one day shows oxygen-related features, that would not be the end of the argument. It would be the start of a much harder one. That is an important warning because this field has learned the lesson the hard way in theory before it could learn it in data. Around small active stars, the chemistry can produce gases that look emotionally exciting long before they are scientifically decisive. Radiation can split molecules, surface-atmosphere exchange can change the balance of gases. Geological conditions can remove some pathways and favour others. So on a red dwarf planet, the same molecule can have more than one story behind it, and one of those stories can look lifelike while being completely sterile. That is why TRAPPIST-1e is such an important test case for false biosignatures. Researchers have not just mentioned this problem in general, they have modelled it directly for this planet. Felton and colleagues explicitly explored false positive biosignature scenarios for TRAPPIST-1e, looking at whether atmospheric exchange could raise oxygen and water abundances enough to imitate a biological signal. And that is exactly the kind of result that belongs in this story, because it shows how deep the problem goes. Even on one of the most attractive rocky targets we know, the chemistry itself can work against easy interpretation. That does not mean biosignatures are useless. It means the context is everything. You cannot take one gas, point at it, and announce victory. You have to ask what the star is doing, what the atmosphere is doing, what the surface is doing, what the escape history is, what the water history is, and what chemical pathways are open or blocked. That is why this gets so unsettling. The more serious the science becomes, the less likely it is that one spectacular molecule will settle everything by itself. Every promising feature comes with a second explanation waiting behind it. And on red dwarf worlds, one of the most dangerous false signals is oxygen itself. Recent modelling for TRAPPIST-1e-like cases shows that oxygen can become much higher than in Earth analogues under the wrong conditions, especially when the inputs that would normally consume oxygen are weak. One of the key pathways is carbon dioxide photolysis. Radiation can break apart carbon dioxide, and if the sinks that usually remove free oxygen are not strong enough, oxygen can build up. So a gas that would sound like a major biological milestone in a headline can instead be the result of stellar radiation and chemical imbalance. That is one of the most important facts in the whole exoplanet biosignature debate, because it takes one of the most emotionally loaded molecules in astronomy and makes it uncertain again. Oxygen can still matter, ozone can still matter, but they do not mean the same thing on every world around every star. On a planet like TRAPPIST-1e, high oxygen could point to life, or it could point to a planet that has been heavily processed by radiation and chemistry. In the worst case, it could be less like a sign of biology, and more like the scar left behind by planetary stress. That is the real warning this section has to deliver. The chemistry on these planets is not neutral. It does not wait politely for us to interpret it. It can actively produce misleading combinations. It can create atmospheres that look suggestive from a distance but fall apart once you understand the stellar environment and the geochemical context. So even a future oxygen-detected headline around a red dwarf would need to be handled with extreme caution. On a system like TRAPPIST-1, the atmosphere can tell the truth in a way that still sounds like a lie, or tell a lie in a way that sounds like the truth. That is also why the current generation of observations has to be described honestly. Webb is not likely to solve the life question on these planets. NASA has been clear about that. The telescope can help determine whether TRAPPIST-1 planets have atmospheres and begin to constrain their chemical compositions, but it is not likely to detect biosignatures on these worlds in a decisive way. That line matters because it keeps the scale right. The current phase of the science is not we are about to announce life. The current phase is we are finally figuring out which rocky red dwarf planets even remain serious enough to deserve that question later. That is not a smaller goal. It is the foundation for the whole field. Before you can talk responsibly about life, you need to know whether the planet has air. What kind of air, how stable it is, how the star affects it, and whether the chemistry can be understood well enough to avoid fooling yourself. TRAPPIST-1e matters because it sits right at that boundary. It is not yet the planet where life can be claimed. It is the planet where the rules for making that claim are being stress tested. And that is why the chemistry problem makes the whole story more intense instead of less. People often think uncertainty goes down in a straight line. First you detect the planet, then you detect the atmosphere, then you detect the gases, then you detect life. But for a world like TRAPPIST-1e, the chain is not that clean. You might detect gases and still be stuck. You might detect oxygen and still be stuck. You might detect something that looks very exciting and then spend years arguing over whether it came from biology, photolysis, geology, or atmospheric escape history. In other words, more data does not always give you a simpler universe. Sometimes it gives you a more deceptive one. That is what makes red dwarf planets such a difficult frontier. They may be common. They may host rocky worlds in the habitable zone. Some of those worlds may retain atmospheres. Some may even preserve water in stable regions for long times. But when the chemistry starts to look promising, you still have to ask whether the star and the planet together could fake that promise. And that means the line between life and non-life may not appear first as a dramatic clean split. It may appear first as a confusing overlap. So the most unsettling possibility is not just that life might exist on TRAPPIST-1e. The more unsettling possibility is that when lifelike chemistry finally appears on a rocky world around a red dwarf, the first thing we see may not tell us clearly what produced it. We may be looking at biology, we may be looking at radiation-driven oxygen buildup, we may be looking at geology reshaping the atmosphere. We may be looking at the remains of a planet that lost water and changed chemically in a way that imitates habitability. The same signal can sit on top of very different realities. That means the cosmos may not only hide life, it may imitate it. And that makes the search more serious, not less serious. Because now the job is not just to find interesting molecules, the job is to build enough context around those molecules that we can tell whether they mean what we want them to mean. TRAPPIST-1e is one of the places forcing that lesson the hardest. And once you realise that, the whole architecture of the system starts to matter even more. Because if formation history controls atmosphere history, water history, and chemical interpretation, then the planets are not just sitting there by chance. The way this system was built may already contain part of the answer. The TRAPPIST-1 system looks wrong the moment you put all the orbits on the screen together. The planets go around their star in about 1.5 to 18.8 days, and all 7 of them fit inside a region smaller than Mercury's orbit around the Sun. That is not just a fun comparison. That compact layout is the reason this system is so intense scientifically. It is why the planets keep tugging on each other strongly enough for us to measure. It is why the transits are frequent enough to build up real data. It is why the system looks crowded, unstable, and almost too tight to be believable, while somehow remaining stable over long timescales. This is not a looser solar system with smaller worlds. It is a tightly packed structure built on a completely different scale. That is the first thing to understand here. The weirdness of TRAPPIST-1 is not only in any one planet. It is built into the architecture of the whole system. In our solar system, rocky planets are spaced much farther apart, the years are longer, and the geometry feels easier to accept. In TRAPPIST-1, everything is compressed. The worlds are close and the interactions are stronger, and the timing matters more. That makes the system look almost mechanical. Not because it is simple, but because everything is linked closely enough that one planet can affect the others in ways we can actually track. And that brings you to resonance, which is one of the most important clues in the entire case. The planets in TRAPPIST-1 are not just randomly packed together. Work from 2017 showed that the system, including the outermost planet H, is connected through a complex chain of 3-body resonances. That sounds technical, but the meaning is straightforward. The orbits are linked by repeating timing relationships. The planets keep returning to certain patterns instead of moving in a completely unstructured way. And that matters because resonance preserves memory. It tells you the system probably did not end up like this through random late collisions and chaos alone. That is a big shift in how you think about TRAPPIST-1e. It is not just a rocky planet that happens to sit in an interesting place today. It is part of an organized structure that likely moved through the protoplanetary disk in a fairly ordered way. The resonance chain suggests migration. It suggests that the planets formed and shifted inward or rearranged while still interacting with the disk. So when you look at Planet E now, you are not just looking at its current orbit. You are looking at the outcome of a formation history that may still control its water budget, its atmospheric starting point, and even its chances of habitability. That alone would already make the system unusual, but newer formation work made it even stranger. A 2024 two-step formation model argued that the inner 4 planets, including TRAPPIST-1e, likely started in a tighter 3-2 resonance chain and later relaxed into the current pattern, including ratios like 8-5, 5-3, and 3-2, as the inner edge of the disk moved and the system evolved. That is a very important detail because it says the architecture we see now may not be the original one. It may be the leftover structure from an earlier and even tighter arrangement. In other words, the present system may be the residue of a changing disk boundary and a staggered assembly process rather than a single clean formation step. That makes the whole setup feel much more deliberate from a physics point of view. The system was not just assembled, it was shaped over time by migration, disk evolution, and linked orbital adjustments. That matters because once the architecture stops looking accidental, the planets stop looking independent. Their histories are connected. If the inner edge of the disk moved, that affects how the inner planets were parked. If migration happened in a coordinated way, that affects what materials the planets had access to. If the system passed through different resonance states, that affects tidal histories and thermal histories. So the orbital pattern is not just about timing, it is about inheritance, and that is the bridge to the atmosphere question. Formation history controls atmosphere history more than people often realize. If the planets formed with a limited volatile budget, then TRAPPIST-1e may have started out with less water and less carbon to work with. If migration brought volatile-rich material inward, then E may have been seeded more generously. If the siblings share related compositions because they came from similar zones or followed similar pathways, then what we learn from B, C, D or F feeds directly back into how we interpret E. That means the atmosphere debate is not only about what Webb sees now, it is also about reconstructing a planetary childhood that may still decide whether liquid water is possible today. That is one of the most powerful things about this system. The present is measurable, but the past is still inside it. The resonance chain is part of the record. The densities are part of the record. The differences between the planets are part of the record. The atmosphere limits on C and D are part of the record. The possible stripping of B is part of the record. Everything feeds into the same broader question: what kind of raw material did these worlds begin with? How did they move? And which of them had any real chance to keep enough of the right stuff? Once you see the system that way, TRAPPIST-1e becomes more than a good target. It becomes one outcome of a planet-making process. That is why this section matters so much. If it were just one lucky rocky planet in one strange system, the implications would still be interesting, but they would stay relatively contained. But if TRAPPIST-1e is the product of a common kind of formation pathway around small stars, then the meaning expands fast, because red dwarfs are everywhere. Compact multi-planet systems around them are not rare curiosities in principle. They may be one of the galaxy's standard ways of building planets. That is the real statistical danger in this story. If systems like this can produce tightly packed chains of rocky worlds efficiently, and if even one member of such a chain can hold on to enough atmosphere and water to remain habitable, then the number of plausible living world candidates in the galaxy could jump dramatically. Not because every planet in every red dwarf system works out, but because the production line itself may be common. One survivor in one kind of common architecture is enough to change the odds in a serious way. And that is why this whole system was built like a trap. Not a trap in the science fiction sense, trap in the statistical sense. Everything about it looks difficult, harsh, unstable, and easy to dismiss at first. The planets are too close, the star is too active, the climates are too strange, the signals are too weak, the chemistry is too deceptive. But if one planet in this kind of setup still ends up being viable, then all of those reasons people used to downgrade red dwarf worlds stop working as cleanly as they used to. The system stops looking like an exception and starts looking like a warning that we may have underestimated a huge amount of galactic real estate. That is the title payoff here. The unsettling part is not just that TRAPPIST-1e may be habitable. The unsettling part is that it may be one member of a broader class of worlds produced by a formation process the galaxy can repeat over and over. If that is true, then the Milky Way may contain far more plausible rocky worlds around tiny stars than the cautious view is comfortable admitting. And if that is true, then the search for life does not just get bigger, it gets much more crowded. That is also why the next stage matters so much more than a normal follow-up campaign. The field is no longer asking whether TRAPPIST-1e is merely interesting. The field has already decided it is important enough to spend a huge amount of precision observing time on. And what happens in those next observations may matter more than the entire last decade of build-up. At this point, the field is done treating TRAPPIST-1e like a speculative curiosity. That phase is over. You do not commit a 15-transit specialized Webb program to a planet that scientists think is probably a dead end. You do that when a target is difficult, important, and still very much alive scientifically. That is exactly where TRAPPIST-1e sits now. Natalie Allen and collaborators laid out a program built around a very specific goal. Find out whether TRAPPIST-1e has an Earth-like mean molecular weight atmosphere containing carbon dioxide. That is not broad fishing. That is a direct attempt to answer one of the hardest questions in exoplanet science, with a strategy designed around the specific problem that has blocked progress so far. And that specific problem is the star. For years, the main obstacle has not been the idea of an atmosphere by itself. It has been the fact that TRAPPIST-1 keeps contaminating the signal. Spots, flares, magnetic activity, and changing stellar surface features can all distort the spectrum in ways that make the planet look flatter, stranger, or more ambiguous than it really is. So the new program is important not just because it adds more observations, it matters because it changes the logic of the attack. Instead of only trying to observe Planet E harder, the team is trying to outsmart the star. That is where the method becomes one of the best twists in the whole story. The plan uses close transits of TRAPPIST-1b and TRAPPIST-1e. Planet B is likely airless or close to it, which makes it useful in a completely different way from E. If B passes in front of the star and mostly carries the contamination signal from the star itself, then E, observed close in time, carries that same stellar contribution plus whatever atmospheric contribution might belong to E. Compare the two carefully enough, and the features unique to E become more believable. In simple terms, the dead-looking inner planet may help clean the evidence for the one everyone actually cares about. That is an unusually elegant solution. The same compact architecture that made the system messy enough to be difficult may now be part of the reason it can be solved at all. The star forced the observers to get clever, and the planetary family structure gave them a way to try. This is not just more telescope time being thrown at a problem. This is a more model-independent strategy for separating the star's fingerprints from the planets. After years of the host star ruining the atmosphere question, the system itself is being used as the correction tool. That is why these next observations may matter more than the last decade of build-up. The earlier years established the target, measured the planet, ruled out easy hydrogen-rich paths, exposed the contamination problem, and narrowed the surviving possibilities. But the new program is built to do something sharper. It is trying to collapse the ambiguity between a flat line and a real heavy atmosphere by using the one thing the earlier work did not yet fully have: repeated close paired measurements that exploit the structure of the system itself. That is a major step forward, because the field is no longer just collecting more data in the same way. It is trying to remove the main source of confusion at the level of method, and the promised payoff is huge. In the 2025 and 2026 program work, the team argued that with 15 closed transit observations, their simulations show they should be able to detect an Earth-like mean molecular weight atmosphere on TRAPPIST-1e at a confidence level of delta log evidence 5 or greater, if the stellar contamination can be corrected successfully with the close transit method. That if matters. It keeps the whole claim honest. This is not guaranteed. It is not a promise that the mystery disappears on schedule, but it is still one of the clearest countdowns in the entire story. There is now a defined observing strategy, a defined target, and a quantified success threshold. That changes the emotional shape of the science. Before this, the future could sound vague. More observations, more work, maybe better answers later. Now the field has a specific plan with a measurable goal. That is why these next 15 observations feel so heavy. They are not just another chapter, they are a test of whether the current generation of exoplanet science can get a credible answer out of one of the hardest realistic rocky targets we have. If the method works, the ambiguity starts to break. If it does not, the field may be facing a much longer and more difficult road than even the cautious view hoped. And the caution is still necessary, because even this smarter plan can be ambushed. The same team showed that strong stellar flares can break one of the core assumptions behind the close transit correction strategy. The method works best if the star stays similar enough between the transit of B and the transit of E for the contamination signal to be meaningfully compared. But if the star flares hard or changes too much between those observations, the correction can fail or become much less reliable. So even the rescue plan enters a dangerous zone immediately. You can build a better subtraction method, and the star can still move the target. That is exactly the kind of complication that makes TRAPPIST-1e feel so important and so maddening at the same time. In their first 3 observations, the team found that the cleanest case increased the preference for a flat spectrum over the original E spectrum after contamination removal. That does not settle the planet as airless. What it does show is how sensitive the conclusions can be once the stellar effects are treated differently. Small decisions in analysis can propagate into very different atmospheric interpretations. That is not a sign that the science is weak. It is a sign that the signal is living right at the edge where precision, method, and stellar behavior all matter at once. This is why the next breakthrough may not come from a bigger telescope or some dramatic new molecule. It may come from subtracting the star more intelligently than before. That is the real bottleneck now, not finding TRAPPIST-1e, not proving it is rocky, not showing it sits in the right orbital zone. The bottleneck is separating a tiny planetary signal from a star that refuses to stay quiet. If the close transit method works, then the surviving options may finally begin to collapse in a meaningful way. If it does not, then even more observing time, more advanced instruments, or entirely new approaches may be needed. And that is why the next few years matter so much. This is not just another incremental observing campaign. It is a decision point for the planet's role in astronomy. TRAPPIST-1e may become the first temperate rocky exoplanet with a credible atmosphere detection built on contamination-aware precision work. Or it may become the most famous unresolved maybe in the entire field. The world that stayed important, measurable, and frustrating for far longer than anyone wanted. Either outcome would be historically important, but they mean very different things for red dwarf habitability, for atmospheric survival, and for how close we really are to identifying another truly promising Earth-sized world. That is the penultimate edge of the story. The target is good enough, the telescope is powerful enough, the strategy is smart enough, but the star is still difficult enough that none of that guarantees success. The answer may finally start to emerge from better subtraction instead of louder evidence. And if that sounds less cinematic than a giant discovery headline, it is actually much more serious. Because this is what the frontier really looks like when the questions stop being broad and start being precise. And that brings the story to the final step. Once all the hype, all the caution, all the null results, all the remaining possibilities, and all the new observations are on the table, you still have to end the right way. Not by lying, not by saying scientists think there is life there, but by saying something more accurate, and in the long run, much bigger. Here is the honest ending. Scientists do not think they have found life on TRAPPIST-1e. That claim is not supported. What the science actually supports is more disciplined, and in some ways, more important. TRAPPIST-1e is one of the best places we have ever found to test whether a rocky planet in the habitable zone of a red dwarf can keep an atmosphere that might support liquid water. That is the real claim. Right now, the data rule out thick hydrogen-rich atmospheres, but they still leave two very different possibilities alive. A bare rocky world, or a world with a heavier atmosphere that is subtle, hard to detect, and still not securely identified. That is the factual core of the story, and it is already big enough. You do not need to exaggerate it. A rocky planet around a violent small star, close to Earth in size, still sitting in the serious atmosphere debate after all this work, is already one of the most important exoplanet cases we have. The reason it matters is not because the answer is dramatic right now. The reason it matters is because the answer is still open after real measurements, real telescope time, real climate modelling, and real elimination of easier scenarios. TRAPPIST-1e has survived the stage where many planets stop mattering. So what would count as a real milestone from here? Not a vague headline, not a suggestive sentence. A real milestone would be a repeated spectrum corrected for stellar contamination that consistently favours an atmosphere over a flat line. That would be the first real step. After that, scientists would want stronger identification of the bulk gases and some pressure-sensitive context that helps show what kind of atmosphere it is. Only after that, much later, would anyone responsible even begin talking seriously about biosignatures or chemical imbalance as a life question. NASA has already been clear that Webb is unlikely to detect biosignatures on these planets. That means the current frontier is not, did we find life? The current frontier is much more basic and much more important. Does a temperate rocky planet around a harsh red dwarf actually have air? That question sounds smaller only if you do not understand what hangs on it. If the answer is yes, then TRAPPIST-1e tells you that rocky planets around the most common stars in the galaxy may be able to keep atmospheres under conditions many people once treated as too hostile. That would widen the map of plausible habitable worlds in a serious way. It would mean the galaxy may contain a huge number of planets that do not orbit calm sun-like stars, do not look comfortable by human standards, and still remain physically relevant to the life question. It would mean the old search image was too narrow, and if the answer is no, that is not a small result either. That would sharpen the opposite case. It would suggest that red dwarfs, for all their abundance, may produce far fewer lasting habitable surfaces than raw planet counts make it sound. It would mean that finding Earth-sized planets in the habitable zone of small stars is not enough by itself, because the star may erase the atmosphere or the water before habitability can persist. That would push the search in a different direction and change how we rank a huge part of the galaxy. So either answer matters at the level of statistics, not just one planet. That is the real meaning behind the title. The terrifying part is not maybe there is life there as a cheap mystery line. The terrifying part is that one world about 40 light-years away can change the math of cosmic loneliness in either direction. If TRAPPIST-1e kept enough atmosphere to matter, then the galaxy may host many more viable rocky worlds than the cautious view allowed. If it did not, then one of the most common kinds of planetary environments in the Milky Way may be much less biologically useful than people hoped. Either way, the result does not stay local. It changes the odds. And the right way to end this is not by pretending the uncertainty has gone away. The uncertainty is the point. Humanity built the most capable space telescope ever launched, pointed it at one of the best rocky exoplanet targets in the sky, and still found that the hardest part was not just the planet. It was the star, it was the chemistry, it was the tiny size of the signal. It was the fact that even good data can leave multiple realities alive at the same time. That is not failure. That is what the real search looks like when the target is actually worth taking seriously. TRAPPIST-1e is forcing astronomy to be honest at a very high level. It is showing that rocky exoplanet science is no longer in the phase where discovery alone is enough. Now the problem is interpretation. Now the problem is separating a heavy atmosphere from a bare rock under stellar contamination. Now the problem is learning whether water survived, whether chemistry can mislead us, and whether habitability can exist in forms that do not look remotely familiar. That is a harder kind of science, but it is also the kind that changes entire fields. And that is why this world stays so important. Not because it gave us a satisfying answer, because it refused to collapse into a simple story. It stayed alive after Hubble, it stayed alive after Webb's first Sirius spectra. It stayed alive through the false start atmosphere possibilities, through the tidal locking fears, through the water loss fears, through the chemistry traps, and through the family comparison with the other planets in the system. Every time the field learned more, the planet became less vague and more consequential. So the clean ending is this. Scientists are not saying there is life on TRAPPIST-1e. They are saying this is one of the best worlds we have for testing. Whether a rocky planet around a red dwarf can remain physically habitable at all. That is where the frontier really is. Not life confirmed, not life ruled out, atmosphere or no atmosphere, survival or failure. A live test of whether one of the most common classes of worlds in the galaxy can stay in the game. And maybe that is the part that should stay with you. Maybe the terrifying part is not that there is life on TRAPPIST-1e. Maybe the terrifying part is that after everything we have learned, the universe is still pointing toward the possibility that life-friendly worlds might emerge in places so hostile and so alien and so hard to read that we have been underestimating reality the entire time. And if that is true, then TRAPPIST-1e is not just a planet. It is a warning that the cosmos may be stranger, fuller and less built around human expectations than we were prepared to accept. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.